Hello, thank you for watching this lecture video. So today is the Thanksgiving Eve. So many of you prefer have lecture video instead of in-person class. Okay, so because in this way you can arrange your family party in a flexible way, right? So I just made this lecture video. So thank you for watching. Okay, so today's topic is many sample problems. Okay, so we just discussed two sample problems. Like a two sample problem, just like this one, like compare two classes. So what is many sample problem? So many sample problem is just like compare many classes, like compare 3 classes or compare 4 classes. So then those things we call this many sample problems. Okay, so at first let's review for two sample problem. So for two sample problem, we say we just convert those problem as testing problem, right? So the hypothesis is HO is no difference. HA has difference, right? Or more specifically, mu1 is larger than mu2, or class 1, because here I wanted to prove class 1 perform better than class 2, right? Okay, so then so first step is set the hypothesis. Then second step is calculate a test statistic. Okay, then determine this test statistic is big or small. Right? So here we have two formulas for test statistics. So I just write down the two formulas. This t value or test statistic equal x bar minus y bar. So okay, so here S1 square over N1 plus S2 square over N2. Okay. Or we can use this, x bar minus y bar over SP, then square root of 1 over N1 plus 1 over N2. So here we have two formulas for test statistic. So here we have the question, which one, right? Which one? Which one we should use? Okay, so difference is, say this one, we assume values equal. So this one, we do not assume values equal. So which one we should use depends on question. So here, let's say we want to compare two classes. So here, I'm sorry. So here I say with, okay, with the assumption. So here we have two, with the assumption of equal values, or we do not say, we do not have this assumption. So here, let's say, suppose we use this with the assumption, okay, with the assumption of equal values. If we have this assumption, then we should use this one, right? Okay, so we just use this one. Okay, so here we need to find this SP. So we call this SP is a pooled standard deviation. So pooled means put them together. So we have a pooled standard deviation and pooled variance. So what is the pooled variance? So that's SP squared. The pooled variance, we say the weighted average for those two variants. So we have those two variants, 7 squared and 9 squared. Standard deviation is 7 and 9. Then variance is 7 square, 9 square, right? So we say we need to find the weighted average for these two numbers. So weighted on what? On the degree of freedom. Okay. So this degree of freedom is n minus 1. So here n 25. So the n minus 1 is 24. So 24. So wait for this. Wait for 24. And for this one, wait for, let's say, 20, right? 20 is a 19 degree of freedom. So we say weighted on the degree of freedom, 19. Okay, then totally is 43. Okay. Okay. So we also can put this like just 24 multiply 7 square plus 19 multiply 9 square divided by 43. So we get this number. So this is the poured variance. And then take square root is a poured standard deviation. We say poured is put together, right? Poured. Okay. So we just put it together. Okay. So we find that t equals this number. Okay. So then we determine this is big number or small number. Then we need to find t critical value. We need to compare this with t critical value. So we need to find this t critical value. So this t critical value from, so we need to get this from t table. So for t table, at the first, what is degree of freedom? So we say degree of freedom is, so degree of freedom in this case is 43, right? This denominator is degree of freedom, 43. Okay. Degree of freedom is 43. And one tail, two tail, or one tail, right? One tail. And one tail, the alpha is 0.005. So we can, so based on this information, you can find this critical value. Okay, so t critical value, so check the t table. Let's say degree of freedom 43. Okay. But we do not have a 43. So say degree of freedom equal 43. But we do not have 43, then we just pick 40. Okay. Okay. So we then one tail 0.005. So which column is for one tail 0.005? Okay. So one tail 0.005. Okay, so this one. Okay, so one tail 0.005. So let's say this one. This column. Okay. So one tail, yeah. Okay, so we find, okay, this 1.684. So this number is critical value. So we use this number to judge if this test statistic is big or small. 1.684. So I put it to here. 1.6. So 1.684. Okay, so this is critical value. This is t value. So compare with this. Now we can say this is small. Right? This number 1.26 is small number. So if this is small number, so we can say, oh, difference is not so big. Difference is not so significant, and we can we make this. So our conclusion is these two classes, the difference is small. Basically, we can say these two classes perform quite the same. Okay. So if I teach class 1, other professor teach class 2, so we say, so based on this data, so I cannot say our class or my teaching is better or our class perform significantly better than others, not better than other class, right? Okay. Okay. So here we say we have two formula for test statistic. Okay. So why we use this two formula? Because we say this formula is, we say this roughly follow t distribution, not so precise. So this one is exactly follow t distribution. So why this one not follow t, this one exactly follow t? So because this is, we replace two sigma, sigma 1, sigma 2, replace two sigma by S1, S2. Like we replace two sigmas. So this case, we just replace one sigma, right? If we assume sigma 1 equals sigma 2 equals sigma, then we just replace this sigma by SP. Okay, so we just replace one sigma, then we have exact t, right? Okay. So this is for two sample problem. Then for many sample problem, so we know what is a many sample problem. So this one is a many sample problem, right? We like compare. Suppose here we have 4 classes, 4 sections for Math 2526, and I teach class 1, and my class average 84. So we find, oh, other class is 81, 82, 80. So I really wanted to say my class perform better than other class, right? So can I see that? So we need statistical proof. Okay, so for many sample problems, we say a basic assumption is variance equal. A basic assumption is equal variance. Variance is equal. So why we need set this assumption? Because from two sample problem, we find if even for the compare two sample, if we do not assume sigma 1, sigma 2 equal, so we should replace two sigmas. So replace two sigma, saying that test statistic follow which distribution. Oh, this is a really complicated problem. So if we replace like 3 sigma or 4 sigmas, those things follow which distribution or which table we should check. So this is too complicated or too difficult. So we just to make things simple, we just assume variance equal. Okay. Okay. So we say for compare many samples, we always assume variance equal. Like okay, so we say sigma 1 from class 1. We say if we compare 4, we assume that sigma 1 equals sigma 2 equals sigma 3 equals sigma 4 and equals sigma. Okay. Okay. So now we have this question: so how to estimate this sigma? How to? And if we want to replace this 1 sigma, by now we have only 1 sigma. So how can we replace this 1 sigma? So again, we just use just like a two sample problem. We use poured standard deviation or pooled variance. Pooled variance, and this also we have like then take square root is pooled standard deviation. Okay. So what is a pooled variance? So just like a two sample problem, we say pooled variance is weighted average. Weighted average for those variance. Weighted on what? On the degree freedom. So here we have, let's say, so here we have standard deviations 7, 9, 8, 6. Then variance is 7 square, 9 square, 8 square, and 6 square, right? So we have variance, let me see. Variance is 7 square, 9 square, 8 square, and 6 square. I'm sorry, square. 6 square. So those are variance. Then we need the weighted average, not adding them up divided by 4. So weighted average. So weighted on what? On the degree of freedom. So here, n is the same degree of freedoms is like 24. Then here 19, right? Then 21, then 20. So n minus 1 is the degree of freedom. So weighted on those. Okay, so we know how to find this pooled variance, right? So just equal 24 multiply 7 square, so plus 19 multiply 9 square, and 21 multiply 8 square, and 20 multiply 6 square, then divide by total weight. So total weight is that's 24 plus 19 plus 21 plus 20, right? So just use this formula, we can find this pooled variance. Okay. Okay. So this is question 2. Okay, I'm sorry. Yeah. Okay, but anyway. So we compare, compare many samples. Like here, our purpose, we wanted to prove class 1, my class perform better than other class. So can we use two sample t-test? Like just compare each pair. Can we do that? Like we compare class 1, compare class 1 with class 2, class 1 with class 3, class 1 with class 4. Can we do that? So answer is yes or no. Sometimes yes. So let's say here logically is if we wanted to compare, if we wanted to say class 1, this one is better than other class, this one is the best, then we need to check they are different, not the same. If they are quite the same, if there's 4 classes quite the same, then we don't need to check the detail, right? If they're quite the same, then we pick the best one. This makes no sense, right? Like 4 classes quite the same, so which one is the best? No best, right? Okay, so in order to find the best or determine which one is the best, we need to check whether we have best one, right? So whether they are equal, or they are quite the same, or have a difference. So at the first we need to check this. So we say for many sample problems, at the first we need to test this. All are quite the same. Like here mu1, mu2, mu3, mu4, quite the same. No much difference. Okay, so the story is if HO is true, then no need to compare. Well, no need to compare for them more. We cannot, if HO is true, this means no best one, right? So if this is true, so compare mu1, mu2, or compare mu1, mu3, then make no sense, right? Okay, so how can we check HO? So can we use like compare 2 by 2 like so let's check this. If let's compare this mu1, mu2, and then compare mu2, mu3, then mu3, mu2. Is this okay? We say this not okay. So so why? So mathematically, if we say if mu1 equal mu2 and mu2 equal mu3, mu3 equal mu4, then mu1 equal mu2 equal mu3 equal mu4, right? But we say in statistics, this is not true. So why? So because in stats, no exact equal. We say in stats, like let's say in stats, A equal B means A minus B. Their difference is quite small. For example, we assume that if that difference is less than 0.001 or less than 0.1, if that difference is small, we believe A equal B. No, or A or B, no much difference, right? Okay, so now let's say we say this number and 1.05, so we can regard this as equal, right? Because there's a two number difference is less than 0.1. Okay, and then 1.05 and 1.10, we can regard this as equal, right? And then 1.10 and 1.15, this is also equal. Okay, but we say 1 and 1.15, like those are not equal, right? So this is just the difference between math and stats. So in mathematics, equal means exact equal. So in stats, equal means difference is small, right? Okay, so for this reason, we say we cannot use two-sample t-test. We just cannot use that method to compare, to check, to test HO. So how can we show those four are quite the same? So we cannot use there's a two-sample t-test. So we need a new method, a new way. So this new way we call it ANOVA. So we say we will use ANOVA for many sample problems. Okay. So what is ANOVA? What is ANOVA? So ANOVA actually is this. ANOVA is analysis of variances. Okay, so I just pick those few, like the head, right? So ANOVA just come from this. Okay, so let's consider general setting for many sample problems. So many sample problems, suppose we have k samples or data like that, or we have, or we can say we have k sets of data. So from this sample, we have those numbers. From this sample, we have these numbers like this, right? So our purpose, if we have many, we want to usually want to compare them, and we want to find the best one. Okay, so we want to find the best one. But before we try to find the best one, we need to answer this, check this question. Is there a best one? So this means that if they're quite the same, no much difference, then no best one, right? So let's recheck this. So here all those are quite the same, so no best one. And have the best one only HA is true. If this not all are same, then maybe we can if the HAs not all are equal. If we reject the HO, then we can check for them more. So maybe we can say like to say like for example, we have 4 classes. Maybe we also can say this like best one maybe also not. Maybe sometimes best one exist. Like this one is the best. Like okay, 1, 2, 3, 4, 2, 3 or 4 could be like that. Class 1 is the best one. Then class 2 and 3 quite the same, but they are better than class 4, right? So we can get this conclusion. Okay. So sometimes conclusion like this. Let's say for 4 classes, maybe class 1 and 2 quite the same. Class 3 and 4 quite the same. But class 1 and class 2 they are same. But class 1 is better than class 3, right? So we can find groups. We can split as groups. So this group is better than that group. So best one we cannot find, but best one maybe class 1 can be regarded the best one, and class 2 can be regarded the best one, because class 1, class 2, no much difference, right? Okay, but anyway, for those kinds of problem, at first we need to check HO. They are quite the same. Okay. So we say check HO, test HO, we use ANOVA. So ANOVA is an analysis of variance. So what analysis means? Means we split those variance into parts. Okay? And so let's check variance. So here the variance we're talking about samples variance, so data's variance, right? We have data, so we can have variance. So this one, the variance is we have this formula xi minus x bar square, add them up, right? So divided by n minus 1. So here if the data like this, we just put all the data together as one data. Then we can find the variance. And so we denote this numerator is AST. So AST stands for, AST is just equal summation xi those data minus x bar square. So we call this as AST. And AST stands for this, for sum of square of total. Okay, AST. So analysis of variance means we can split AST into 2 parts. AST equal, we can split AST as SG plus A says E. So what is A says G? What is A says E? So the story is like that. We have like 4 classes of some class. So we put data like that. Like okay, so we say group 1, we have data, right? And group 2, we have data. Okay. And then like our group K, our class K, we have data, right? So we want to split all data into 2 directions. This direction, changing this way make a difference, or this direction. Okay. So when we consider the changement in this direction, we assume in this way, this direction no change. So in this direction no change means those numbers all are same. Right? So in this way no difference, no changement. So only the changement come from this direction. So this direction changement of values, we call this as SSG. So we call SSG means the sum of square from group. Okay, and so the changing only in this direction, we call this as SSE. Okay, so here SSE means the sum of square of arrows. But here arrows means not so clear. This actually this name is not so precise. So some textbook prefer use this. This is between groups. This is between, and this way the is within, like within each groups. So say this is is within. Okay, so this direction is between. Okay. 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 So we just okay. So the idea is if A says G is small, then there's small. What does this small mean? Small means between group to group, difference small, no much difference. Then we say H is true, right? Okay. Then okay. So once we have the SSG, how can we determine this number is a big number or small number? So at first we need to standardize this. Then check a table, right? So just like a general normal to standard normal. So we use this SSG. So we standardize SSG. We need to compare with SSE. Okay. And this SSG have degree of freedom, so we should divide by their degree of freedom, so as the average, right? So degree of freedom divided by the degree of freedom. So here we have 2 degree of freedom, df1 or degree of freedom in numerator and degree of freedom denominator. So we have this number as a test statistic. So then which table we should check? So we will check the F table, we call it. Then, and we call this test statistic as F value. Okay? So then check the F table, so determine this number is big or small. So if this F value is big, then means all the difference is significant, right? If this if value or this test statistic is small, then we say no much difference, or difference is not so significant. So again, how to determine this test statistic or this F value, big number, small number? So we need to compare critical value, right? So this critical value, we need to check F table, and we call this critical value as F critical value, right? Okay, so here let's say, so here, so those kind of, so here the key point is just calculate the test statistic. Then determine the test statistic is a big number, small number, right? So here we need to understand how can we calculate S is G, S is E, how can we find this F value, how can determine this F value big or small, right? Okay, so now let's use this very simple small data for explain how can we find S is T. Let's check the ANOVA. ACT can be split. Let's check this S is T. We can split that as S is G plus S is E. So let's confirm this for this small data or simple data. So S is T means we put the data together. So like data becomes this. So here we have three groups. Sample 1 data is 1 to 3. So sample 2 is 4, 5, 6. Sample 3 is 7, 8, 9. So data like that. Then how to find S is T? So we put those data together. So it looks like we have one sample data. The data like this. Then each number minus x bar. So x bar is 5. So S is T equal each number x. S is T just equal this. Equal summation xi minus x bar square, right? So each number minus 5 square. So first number 1 minus 5 square. Then this number minus 5 square like this, right? Okay. Okay, so we say, so 1 minus 5 is 4, so 4 square, so plus 3 square, right? 2 minus 5, and then 2 square, then 1 square, then 5 minus 5, 0 square, right? And then just repeat. 6 minus 5, 1. Then 7 minus 5, 2, right? So just like that. Okay? So this is S is T. Okay? Okay, so we can easily find this S is T equals 60. Right? So this is S is T. So then what is S is G? S is G, let's say data is, we have 1 to 3, we arrange the data like this, 1 to 3, 4, 5, 6, okay, 7, 8, 9, okay. So S is G is, we say, we just check the change from this direction. So we assume in this direction, no change. So arrange the data in this direction have change, right? So we make in this direction no change. So means no change. So we have to replace those data 1, 2, 3 as 2, 2, 2. Okay. 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 So in this direction, no change, right? They're the same. And 4, 5, 6. So we just replace data by 5, 5, 5. just replace data by, we say, group mean. Just replace data by one number. So which number should it be? So usually the average, right? And then like here 7, 8, 9, so we replace the data by 8, 8, 8. Okay. So for those data, in this direction no change. The only changement come from this direction, right? So this is SSG. So SSG is just like SST with data like this: 222, 555, 888. Okay, so find SSG, just find SST for those data. So formula is the same, like each one minus x bar square. So x bar average is still 5, right? So 2 minus 5 square, 2 minus 5 square, 2 minus 5 square. So we have 3 of them. So just 3 times 2 minus 5 square. So then for 5 minus 5 square, 5 minus 5 square, 0, 0, 0. Then 8 minus 5 square, 8 minus 5 is also 3 multiply 8 minus 5 square. So we find this number is 54. So this 54 is SSG. Okay? So you understand what SSG means, right? Okay, so SSG, we just assume in this direction no changes, then all changement, all variance just come from this way. Okay. Okay, so now what is SSE? So SSE is, we just check the changement from this direction. Okay, so data is like 1, 2, 3, 4, 5, 6, okay, 7, 8, 9. So we just check the changement from this direction. Okay, so we just say, we just check out 1 to 3 variance. So 1 to 3 variance. So we just have these 3 numbers. So their variance. So their average is 2. So each one minus 2 square. Right? So 1 minus 2, 2 minus 2 square, 3 minus 2. So just the 1, 0, 1, right? Okay. And for this one, 4, 5, 6. So their average is 5. So each one minus 5 square. Just xi minus x bar square, right? So 4 minus 5 square, 1. 5 minus 5 square, 0. So 6 minus 5, 1. So here's 1, 0, 1. So here's the same, 7, 8, 9. So average is 8. So each one minus 8 square. So 1, 0, 1. So we find this equals 6. So this 6 is SSE. So we find, for this example, we find SST equals 60, SSG 54, and SSE equals 6. So we find, this is true, right? SST, because 60 equal 54 plus 6. So we say SST equal SSG plus SSE. This is true. So this is unknown. Okay. Okay. So now, so test the statistic. If value. So if value is thus, we say SSG our degree of freedom, then over SSE divided by degree of freedom. Okay, so SSG is 54, SSE is 6. Okay, right? So 54 but it should divide by degree of freedom, and 6 divided by degree of freedom. So how can we determine this degree of freedom, df1 or df2? How can we determine the degree of freedom? So let's say, so we separate. Okay, so what is the degree of freedom for A says G? So A says G, go back, let's say the A says G. How can I find A says G? We assume the data is just like 2, 2, 2, 5, 5, 5, and 8, 8, 8. So here we say, even though we have 9 numbers, but essentially we have 3 numbers, 2, 3, 2, 2, 2, yeah, 2, 5, 8, right? So essentially we have 3 numbers. So if we have 3 numbers, then degree of freedom just n minus 1. So degree of freedom is 2. Okay? So actually, if we compare 3 groups, degree of freedom for A says G is k minus 1. If we have a compare k group, or 3 groups, then just the 3 minus 1, 2. Okay? Okay. So how can find the degree of freedom? So this is equal degree of freedom is G is 2. So this is where the 2 come from. Okay. Okay. So how can you find the degree of freedom for df2? So we say A is T. We split. We separated this A as T. No. Oh. Okay. Sorry. We separated this A as T into, let's say, let me write it down there. Okay, A as T into A as G plus A as E. So this is, we call this ANOVA, right? Then we also separate the total degree of freedom. So here, this degree of freedom is 8. Because we put it together, we have 9 numbers, right? So sample size 9. So degree of freedom is 8. Then this A is G, degree of freedom 2, then this degree of freedom should be 6. So if we separate A as T into 2 parts, then we separate the total degree of freedom also into 2 parts. Okay? So if this is 2, then that one is 6. So this is 6 come from. Okay? Okay, so we find this test statistic is this number 27. So then we need to check, is this number a big number or small number? Big or small? So to determine this big or small, we need to check a F table, or we need to find F critical value. Okay? We find F critical value. So we need to check F table. So here is F table. Okay? So this is F table. So for F table, we have 2 degrees of freedoms. So this one is degree of freedom 1. So some textbook call this the degree of freedom in numerator. And here, this is the degree of freedom in denominator, or df2. So let's go back to our problem. Let's say our test statistic, the degree of freedom is 2 and 6. right? 2 and 6. 2 and 6. So 2 is so so degree degree freedom in numerator 2 and denominator 6. Okay, so we get this number. So this is let's say 5.1433. So this is F critical value. Okay, 26. Okay, 26. This number. So use this number. We use this number as a standard to judge a big, giving numbers a big number or small number. This number, let me write it down as 5.1433, right? Okay. So, okay. So over, okay. So use this as our standard. So we can say this is a huge number or a big number. Okay, right? Then we can say, oh, these 3 groups have a significant difference. So 1, 2, 3, and 7, 8, 9. This difference is big. Okay. Okay. So this is so we just explain. So what is ANOVA? What is F value? Okay, and then check F table to determine this F value is big or small, right? Okay, so this is we just use a very small data set. So we call this is artificial data set to explain this ANOVA. Then we haven't solved our problem. Like if we compare the 4 classes, can we say my class perform better than other ones, or should can we say they have a difference? Okay, so for that problem, so we just let's take a short break. Then we will continue. Okay.